Deep beneath the crust, temperatures rival the surface of the sun. A furnace of iron and nickel glows at 5,400 degrees Celsius, yet the planet shows no external fuel. The secret lies in atoms that silently split, releasing heat for billions of years. The inner core is a solid sphere of iron-nickel, 1,220 kilometers across, squeezed by about 3.6 million atmospheres of pressure. Encircling it, the outer core is a liquid layer another 2,200 kilometers thick, composed mainly of molten iron with traces of sulfur and oxygen. Together, these layers leak roughly 13 terawatts of heat each second into the mantle, a flow that fuels mantle convection, drives plate tectonics, and powers the magnetic dynamo that shields the planet. Early models assumed that the heat left over from Earth's violent accretion, energy released when planetesimals slammed together, could sustain this output, but thermal calculations show that such primordial heat would have been exhausted within the first 2 billion years of Earth's history. Yet seismology and high-pressure experiments indicate the core still burns at 5,000 to 6,000 degrees Celsius, hotter than the surface of the sun. The missing energy comes from radioactive decay embedded in the deep interior. Isotopes such as Uranium-238, Thorium-232, and Potassium-40 continuously transform, releasing about 20 TW of heat in the mantle and an additional 3 TW within the core itself. The slow, steady trickle of decay energy, equivalent to the output of roughly 13,000 large power plants, keeps the planet's engine humming long after its birth. Radioactive decay is the slow, steady combustion of unstable isotopes. In Earth's mantle and core, 3 isotopes dominate: Uranium-238, Thorium-232, and Potassium-40. Uranium-238 decays with a half-life of 4.47 billion years, emitting alpha particles and releasing 4.27 MeV per decay. Thorium-232's half-life is 14.0 billion years, giving 4.08 MeV per event. Potassium-40, though only 0.012% of natural potassium, has a 1.25 billion-year half-life and emits 1.31 MeV. Though each atom releases a tiny quantum of energy, the sheer quantity, billions of tons, creates a continuous heat engine. The mantle contains about 20 ppb uranium, 80 ppb thorium, and 250 ppm potassium. These concentrations translate to roughly 9.5 times 10W per kilogram of uranium, 2.6 times 10W per kilogram of thorium, and 2.9 times 10W per kilogram of potassium-40. Summed across the entire mantle, they generate about 20 TW of heat, roughly half of Earth's total surface heat flow. Uranium-238 alone accounts for about 7 TW of radiogenic heat. Its decay chain passes through 14 daughter isotopes, each releasing energy, before ending as stable lead-206. Thorium-232 contributes another 5 TW, following a 10-step decay to lead-208. Potassium-40, despite its modest abundance, adds roughly 3 TW, thanks to its dual decay modes: beta decay to calcium-40 and electron capture to argon-40. Together, these isotopes supply roughly 15 TW directly within the mantle, while a smaller but significant 2 TW originates from the core's trace uranium and thorium. The heat budget is not uniform. Enriched regions like mantle plumes contain up to twice the average uranium concentration, boosting local heat flow and spawning volcanic hotspots such as Hawaii. Conversely, ancient cratons show depleted radiogenic signatures, explaining their tectonic stability. These numbers show that a handful of atoms, decaying over billions of years, sustain the engine that drives continents, oceans, and even the magnetic shield surrounding Earth. Heat from radioactive decay creates temperature gradients that drive convection. In the outer core, liquid iron-nickel expands as it warms, rising toward the mantle while cooler fluid sinks. This churn generates the geodynamo, a self-sustaining magnetic field that extends tens of thousands of kilometers into space. Above, mantle convection cells move at centimeters per year, dragging the overlying lithospheric plates. This slow but relentless motion fuels earthquakes, builds mountain ranges, and fuels volcanic eruptions. The heat flux at the core mantle boundary averages 5 milliwatts per square meter, enough to keep the outer core in perpetual motion. Hot upwellings form mantle plumes, while cold downwellings create subduction zones. The interplay of radiogenic heating and core cooling thus links the invisible atomic world to the dramatic surface geology we observe. Without this convective engine, plate tectonics would stall, the magnetic field would fade, and life on Earth would be unrecognizable. Scientists cannot drill to the core, so they rely on indirect probes. Geoneutrino detectors, such as Japan's Camland and Italy's Borexino, capture antineutrinos emitted during beta decay of uranium and thorium, providing a real-time map of radiogenic heat production. Seismic tomography reveals temperature anomalies by measuring the speed of P and S waves. Slower speeds indicate hotter, partially molten regions. Laboratory experiments on high-pressure iron alloys simulate core conditions, refining estimates of thermal conductivity and thus heat loss rates. Satellite gravimetry tracks mass redistribution caused by mantle convection, offering another window into deep heat flow. Future missions like the proposed Earth Interior Explorer aim to combine neutrino detection with ultra-precise gravimetric data, tightening the error bars on radiogenic heat estimates to within a few terawatts. These tools turn the invisible decay of atoms into measurable signals, confirming that radioactive fire truly powers our planet's heart. The story of Earth's core heat shows how tiny atomic betrayals shape continents, oceans, and the magnetic shield that protects us. Next time, we'll uncover how that magnetic field deflects deadly solar storms. Subscribe and stay tuned for the next deep dive.